nanohub.org.
Online simulation and more for nanotechnology.
Okay, so thank you all for coming today. So this is the first lecture of a class that's just kicking off on fiber optic communications. And so the whole point of this class is going to be to introduce you to like why fiber optics are so important, and then kind of go through some of the key aspects of fiber optics. Today I'll be kind of launching on the whole topic of like how do fiber optic fibers actually work, and what are kind of the key concepts behind fiber optics, like just very broadly. But then I'm also going to touch on like how do you actually turn this into a network, okay? So, but it's going to be a very brief overview. But then later, we're actually going to get into more details about like the kind of different components that are at the beginning and the end of the fiber optics, as well as like what are the fundamental concepts in more detail about the networks. And then we'll talk about like what are kind of the latest and greatest network architectures. And then last week is basically like what are kind of the future of fiber optics. So that's all in the course outline in this last page. Okay, so where does fiber optics come from? So actually this is kind of interesting history in some sense. So how many of you are familiar with the Tyndall effect? Anybody? Okay, so basically Tyndall effect I can illustrate very easily. Okay, so I have two erasers that are full of chalk, okay? So now I'm just going to clap them together. So what do you see? You see a bunch of dust, right? And so that dust is actually coming off the chalk, right? And so that's not anything unusual. But if you actually were to take a laser and actually shine the laser through this, which I don't seem to have at the moment, then you would actually see that there's actually a strong amount of reflection off the laser as it passes through this medium. And you can also see that visually, like just from the reflection of the light from the dust, right? So of course, don't do this too often or it's bad for your breathing, but you can see that basically there's a lot of reflection, especially if you do it near like a bright light source, there's lots of back reflection. Okay, and so that very simple concept, just that dust causes light scattering, actually caused John Tyndall to take things a step further once he discovered that and actually start guiding light in jets of water. Okay, and so basically you can think of it almost like a permanent cloud of chalk dust, but basically it forces the light to actually be guided through this jet of water. Okay, and so this is like kind of like, at this point is kind of a curiosity, but it kind of like spurred the idea of like creating like these fibers, okay? Because basically if you can do this with water, why can't you do this with a solid material, right? And so the idea is actually you can now take a solid material and now guide light through it. And then actually in the early 20th century, Heinrich Lahm actually illustrated that this not only can be done to guide light, but it can be done in a way that transmits images. And so that actually was a significant advance to show that it can preserve the whole like image as you travel through the fiber. So this is actually a high quality form of transmission and communication. Okay, and so then this actually led to the challenge that, of course, like when you touch the fiber or otherwise like interfere with it, the image transmission may not be as good. And so that basically is coming because when you touch the fiber, it can cause scattering and loss, which may be hard to control systematically. And so in order to get better control over that, there was actually introduction of a cladding by Lawrence Curtis. Okay, and so of course at the time, this was a significant advance because it improves the reproducibility significantly, but by modern standards today, the losses are incredibly high. It's on the order of basically 1 dB per meter, which may not sound like a lot, but if you think about like long distance transmission, then it's 1,000 dBs per kilometer. So this is definitely not something you want to do like for a global network. However, within a decade, actually, Corning demonstrated you could get down from 1,000 dB per kilometer to 20 dB per kilometer at visible range, like near red. Okay, and then that actually made it possible to now start thinking about global communications. And indeed, by the 1980s, there was a transatlantic optical cable that was laid between US and Europe. And then there was, of course, a lot of further work on these, and now it's a global network. And of course, undersea cables have also been around for a long time. I won't go through this in as much detail, but just to give you some context, in the 1800s, we were using telegraph cables, and to send a telegraph of like 17 words, okay, that would cost like almost $100, okay, $85, which was a lot of money back then especially, and still is a fair amount of money just to communicate 17 words, right? Imagine if you had to pay $85 per text message. But by the time that we got to the 1980s, then actually the price was coming down like many orders of magnitude. And as you know, most of you have now basically $50 per month plans that allow unlimited texting. And so basically it's too cheap to meter in some sense at this point. So what enabled that, of course, is this global network of fiber optic cables, many of which are under the sea. And so this is actually showing you like what does the network look like today. This was published in Science like a few months ago. And this is actually showing you not only do we have a transatlantic cable, but we also have another transatlantic cable down here. We have lots of connections that are basically within continents, because in some ways it's actually easier to lay fiber in the ocean, kind of parallel to the shoreline, than to cut through the middle of, like, say, the Amazon or something. And then you can also see there's lots of connections to Asia, to Middle East, to Europe, to Africa, Australia, you name it. Basically everything except Australia is connected at this point. So, and then if you look at a kind of more local scale, then you may know that there are actually like a lot of fiber to the home implementations nowadays. This is just one example of a fiber to the home. If you have Metronet or something else as your home internet service, you may have experienced this. Or of course, you may know Purdue also is on a fiber network, which is called Internet 2. And basically what's happening is that there's basically a tie-in from fiber either directly into the home, or fiber goes to a local node and then connects to a coax and then connects through cable modem, okay? And so in either case, you are using fiber. It's just a matter of like, are you connecting directly or indirectly to the fiber? And there are a lot of fibers nowadays, right? Because this is such a really key commercial technology. It's gone beyond just the standard fibers, like number one, but there are like lots of other fibers out there nowadays. And so without going into all the details about every fiber type right now, what I can say is basically there are a few different classes of fibers that we care about. The first type, of course, being data transport. But another one that's very closely related is for signal amplification. And so basically the concept is when you send the light down like this really long cable across the Pacific, say, like that's really thousands of kilometers. So in order to keep the signal at a strong enough intensity so you can actually detect it, you have to have amplification. And so then that often introduces things like erbium-doped fiber amplifiers that basically will take in the signal and then amplify it using re-emission of erbium at a specific wavelength, which is 1550 nanometers. And then there are also other applications still where you basically create fibers out of something similar to erbium-doped fiber amplifier, sometimes like maybe erbium and ytterbium. And then you can actually create like a very, very intense source of laser light. And then that can even be converted into a super continuum source where instead of just a single wavelength, you actually emit a very broad band, like ultra bright white source of light. And then of course, you know, now there's even interest in using fibers to communicate not just information, but also power. So then that's actually an interesting way to communicate power, sometimes called a photonic power converter. And it has some advantages, particularly that you don't have to have a physical coupling between two systems, and you can basically sever any electrical connection. So if you're going from, say, high voltage to low voltage, for example, then you can ensure safety is achieved there. Okay, so basically, I think most of you probably already know what a fiber is, right? So you know what a fiber is, like a core and cladding. right? So I don't have to explain that. So, but yeah, one question is like, do you know basically what is the key difference between the core, the cladding, and the coating in terms of refractive index, typically? Like, what is the kind of order of the refractive index as you go from core to cladding to coating? Anybody know? Is the core the highest index or the lowest index? Highest index, right. Yeah, and so why is it the highest index? Right, exactly. So using the high index allows for index guiding of the optical beam in the middle of the core, right? And so typically this core would have a slightly higher index than the cladding. And so here, basically, I just gave like a kind of a rough range of refractive index differences, like basically fractional difference. So basically, I've quantified this as the difference between core and cladding divided by the core index. Anywhere from maybe like 10 to the minus third up to 0.02 is kind of a standard value, or 2%, right? And so what this is saying is like you use a small difference in refractive index to really keep light well contained within what's typically the core. But of course, you can also have other layers as well. Sometimes in addition to the core and cladding layers, which like I said are essential to basically reproducibility of the fiber, you may also have like a buffer or jacket layer. And the jacket layer typically is not really optically active, but this is more like kind of to preserve what's inside, right? And to prevent any interference like, light or other things coming in to the system, okay? So then next question is, how do we achieve this small difference in core and cladding index? So basically there are actually a few different ways. And sorry, this typo, but for raising the index, typically we can dope glass with small amounts of metals or semi-metals like aluminum and germanium. Of course, lead is option as well, but typically it's more toxic, so it's not as appealing. And you can also do index lowering by adding typically like very light elements that are kind of to the right side of the periodic table, such as fluorine or boron. Okay, and so that means that you can actually readily achieve using kind of a single base material plus some individual dopants, like kind of this range of fractional refractive index differences. As far as losses go, so losses, like I said, are a very key issue because that's what took it from kind of intellectual curiosity to something that's kind of, the backbone of a lot of what happens in the modern day world. And so there are some fundamental mechanisms that control these losses, okay? So I assume most of you are familiar with Rayleigh scattering. Anybody not familiar with that? Okay, so as you may know, like Rayleigh scattering is what causes the sky to be blue. And so typically it means that as you go to shorter wavelengths, you get more and more scattering. So then that makes the sky blue, but then as you go to longer and longer wavelengths, you get less and less Rayleigh scattering, so that kind of goes away to a large extent. That's basically this yellow dashed line here, right? So you see that, you're actually not going to do much better than like maybe 5 dB per kilometer at 700 nanometers. So when they're getting to like 20 dB per kilometer around that wavelength, that was already a really good result because Rayleigh scattering was still there. But then that actually led a lot of the people in this area to realize we need to avoid Rayleigh scattering by basically shifting to infrared wavelengths, okay? So of course it has the disadvantage, you can't see it directly, but it has much, much lower loss, as you can see here. If you go to say like around 1300 to 1400, typically you can get Rayleigh scattering below 1 dB per kilometer, which is considered pretty good. And furthermore, if you go to 1550 nanometers, which is another key wavelength because of the erbium that I mentioned, then you can actually get even below that. However, there are specific absorption mechanisms as well that are associated with using glass, such as the OH radical, which is happening basically like close to 1400 nanometers. And then there's another infrared absorption tail that picks up past 1550. So that's actually why we typically would operate either at 1300 or 1550, because you can see that those are kind of like the low loss regions of this overall spectrum. Okay. So any questions about that so far? Okay, it's all clear. So this is just illustrating this in a slightly different way to show you that the theoretical best may look something like this, okay? But if you just include like kind of like these quote-unquote ideal materials like ZB-LAN, which are not really standard glass at all, then you can actually see you can get like to really, really low attenuations, maybe even as low as like 1/100th or 1% of a dB per kilometer, right? So that's really, really low. However, in practice, it's much cheaper to buy silica, and then that can get to around 1 dB per kilometer pretty readily. But because of the material issues, you can't really operate at as long a wavelength and suppress as much Rayleigh scattering as the ZB-LAN material here. Okay, so ZB-LAN would really be a specialized material, but most of this class will probably talk about silica. Okay, so then another really key aspect of fibers is what's called numerical aperture. So many of you probably already heard of this concept, so it may not be new to you, but basically the way I think about numerical aperture is, you know, what range of angles can I couple into the fiber, okay? And so this acceptance cone is really the key thing, because basically the bigger this acceptance cone is, then the easier it is to couple into the fiber, right? And actually, the key thing that's determining this acceptance cone is the refractive index difference between the core and the cladding, because that's what tells you, you know, at what angles can you send in light from out here and then get it to be index guided in the fiber, basically to bounce off the core cladding interface. Okay, so that's where that's coming from, like that value that I wrote down as square root of n1 squared, which is of course the core refractive index, minus the cladding index n2 squared. Okay, so that's basically the origin of that. So you can see that if n1 and n2 are equal, then your numerical aperture would go to 0. And so that, of course, is not going to be a great result, right? Now, if it's slightly greater than 0, but you have just a small refractive index difference, then you get a correspondingly small numerical aperture, okay? And so basically that means that light has to come in within a narrow range of angles, and then it can be internally guided. If you have a larger refractive index, now you can actually accept light from a greater range of angles, and they'll still bounce back and forth successfully as you would like. So then basically, this tells you that what I've defined as this so-called delta parameter, and let me just draw this on the board real quick. So if we define NA is square root of n1 squared minus n2 squared, but we also assume n1 and n2 are close to each other, then we can actually write something like n1 plus n2 times n1 minus n2. Okay, so you can write it like that. And then we can also assume that n1 plus n2 is approximately equal to 2 times n1. And so then if we take that out, and then we divide this by n1, then we get n1 squared. And so then you basically get something that looks like divide by 2, so that's 2 squared. So it's 2 squared, n1 squared comes out of the square root. Then you get something like square root of n1 minus n2 divided by 2 n1. And so this is typically defined as this parameter delta. Okay, or sorry, I meant to write it differently. So we'll write this as 2 delta here. So then basically what this is telling you is that this delta parameter, which is that fractional difference that I was talking about, is basically going to give you the square root of numerical aperture. So basically, just to give you an example, if we say N1 is like 1.44 and delta is 0.001, just as an example, or let's say 0.01, just to be simpler math. Then we got basically 1.44 times square root of 2 times 0.01. So that's square root of 0.02. And so then that becomes 0.144 times 1.44, which is approximately 2. Or 0.2, just kidding. So 0.2. So that gives you a numerical aperture of 0.2 for like a fairly large refractive index difference. And so if we translate that into the angle now, basically we said the angle is arcsine of the numerical aperture, right? So basically you get your acceptance angle theta A is equal to arcsine of 0.2. And so, although I don't have a calculator right now, I think that's on the order of about 20 degrees. So let's say approximately 20 degrees. So that gives you kind of the range of values of angles that are acceptable. So that does mean that it's a challenge oftentimes to couple into the fiber because we can't just send it from any direction. It has to be the right direction, and also obviously it has to be close to the middle of this core. You can't just send it into here and then expect it to be index guided. Okay, so now the next thing I want to point out is basically this delta parameter, of course, is sensitive to the dopant. And so, of course, like delta is not always 0.01. That was just an example. But it's usually hard to get it to be extremely high. But you can usually make it almost as low as you want, right? So there's no like real lower bound, but there's definitely an upper bound in practice, I would say. Unless you start using totally different material than glass. And now another thing that you can do that's very interesting is rather than just have like what's called a step index grading, where you basically go from a core to cladding directly, and there's no intermediate material, you can also do a so-called graded index fiber. And so in the graded index fiber, the difference is that you just have a continuous change in the refractive index as you go from the core to the cladding region. And so there's kind of like this intermediate thing. And so this also has interesting implications for the motion of the waves through this fiber, okay? So if you send light right down the middle, then actually you can see it oscillates kind of like this. And so this is called like a meridional plane. And so if it goes down this meridional plane, which is down the middle, then basically it oscillates kind of like a sine wave here. And then if you send it kind of off the center of the axis, then it actually follows what's called a helical trajectory. So if you're familiar with the structure of DNA, it actually like kind of goes around in a single helix, which is like 1/2 of a double helix of DNA or maybe like an RNA structure. And then that actually, if you look at it from a top-down view, creates like kind of this series of orbits in different angles. And sometimes those are repeated periodically, and then sometimes it may be technically chaotic and may not be. Okay, so actually both are possible in the graded index fiber. Now, of course, the question becomes like, why would we do this, right? Like, what's the value of doing like kind of a graded parameter instead of just like a step index or something, right? And so basically the reason is interesting, which is if you're sending multiple rays at the same time and they have different wavelengths, let's say, just for simplicity, you know, they may actually travel at different speeds in a step index fiber. However, in a graded index fiber, they can actually be much more closely matched in terms of their speed because the rays in the center are going to travel more slowly, and you can actually continuously modulate the speed as you go to different wavelengths. Basically, the less time it spends in the center, which typically is something that happens as you move away from kind of that central wavelength of guiding, then the speed will actually not vary as much for the overall mode. And you can see that there are a few examples of like these so-called P parameters that determine like how the profile is characterized, like whether it's kind of like a linear profile, so that's P equals 1, P equals 2 is kind of quadratic, and then P equals 5 is quintic, and so on. So just different orders. Okay, thanks for coming. See you later. So now let me talk about the so-called V parameter. V is in Victor. Okay, so basically, why do we care about this V parameter? So the V number tells us how many modes are in our fiber. Okay, so basically the way to look at this is V is directly proportional to numerical aperture, which we talked about earlier, divided by the wavelength times this parameter A, which is the core radius of the fiber. And the V number, okay, so this is just a number at this point, doesn't necessarily have any inherent meaning, tells you how many modes can be present in the fiber at a given wavelength, lambda naught, okay? And so the key thing about this is it's all determined by basically a solution to Maxwell's equations in the fiber. And in particular, since it's cylindrical, there's a particular solution that depends on what's called the Bessel function. And the Bessel function actually tells you that if this V parameter is less than 2.405, then you can only have a single mode. You can't have multiple solutions. However, if V is greater than 2.405, you can have 2 modes or more. Okay, so that basically tells you now if you want to have a fiber that just supports one mode at a given wavelength, you must choose the V value to be less than 2.405. And so that tells you like basically how large the core should be. So then just to give you ballpark now, if you assume numerical aperture is 0.2, then you take 2.405 divided by 0.2, that's around 10. And then you divide that by 2 pi a. So that's like some given radius, let's say 1 micron. So time divided by, let's say 7. So that gives you something close to 1. So then that means that like for a core radius about 1, you can actually have single mode operation around 1.55 microns. Okay, so that's just an example, right? But that tells you that there's kind of an upper value of the core diameter. And the reason that's important is that it's of course easier to make larger core diameters since we're talking about pretty small numbers on the order of wavelength of light. So basically that means if you're in a single mode, then you'll get like a Gaussian with high confinement. So in practical terms, why do we care about this? So this is what enables us to have high data rates. Okay, so of course this is very critical for anybody who ever got stuck downloading a video or other high bandwidth application to have higher data rates. And so if you have a single mode fiber, then of course you can enable higher data rates. But another thing that can be advantageous is you can also have lower power attenuation. And the reason is because now you can optimize the fiber to specifically limit the loss from that one mechanism. Okay? And then the other thing that can be advantageous is sometimes you can reduce what's called modal noise or crosstalk that can cause basically interference between different modes and different channels on the same fiber. So there are a lot of advantages potentially to these. And then this is just showing basically what happens to the so-called effective refractive index as you vary the V number. And so what this is showing basically is like if the V number is very small, so basically that corresponds to basically a 0 size core, then basically nothing is in the core, right? Which makes sense. But as you make basically the core bigger, then the effective index of the mode is close to that of the core. So that means most of the mode basically lives in the core. And so there's kind of this continuous variation. But of course, as V passes like certain thresholds like 2.405 and so on, you start to get additional modes in the system. So this is just showing what's called a band diagram, which is illustrating how fiber works. Have you seen band diagrams before, or should I explain what this is? You haven't seen it? Okay, that's fine. So basically, the band diagram is showing you two things. Like on the x-axis, it's showing you the K value. So this is basically the momentum of light. Okay, so this is basically telling you like how, let's see, how can I say this? It's telling you basically like what its momentum is in a particular direction. Okay, and so in this case, we're talking about its momentum down the fiber axis. Okay, and then omega is basically the frequency. Okay, so this is the y-axis here. And so what this is showing you is that if your momentum is not large enough relative to the frequency, then you're in this so-called radiation mode space. And so in other words, you don't have a confined mode, or it's not index guided. Okay, so this is something you already know, because if you know what index guiding is, you know that if you're not traveling along the fiber, quickly enough, if you're traveling like this angle or something, then it's basically going to leak out of the fiber, right? And so that's what it's telling you here. But also tells you that there are these other modes that are below what's called the light line. Light line is basically like the point at which you basically just have achieved internal reflection. And there are modes that are below that internal reflection that are basically well guided within this core of the fiber optic, right? And you can see that basically as you go to higher V numbers, you start to get more and more of these modes. So that's basically what's happening, because as you go to higher frequencies, it goes to lower lambda naught and thus higher V number. And so this is just showing a couple examples of the types of modes that can be created in this kind of structure or scenario. So basically the first fundamental mode is basically like a Gaussian mode, and it's oftentimes referred to as the HE11 because it's like a TE mode, but it's not exactly TE because boundary conditions are not strictly transverse electric. But there are also like higher order modes such as this LP11 mode, which is not really either TE or TM at all, but it's kind of its own thing that's specific to fibers. And of course, we'll talk about that in more detail later, so I wouldn't expect you to memorize it right now. But basically, the TE modes, strictly speaking, are when the Z component of the electric field is 0. So basically, as you go into the fiber, you see exactly 0 electric field in that direction. And then a TM mode is basically the same for HZ being 0. Okay, but then these hybrid modes that we're talking about, like HE and EH, are basically modes where you have predominantly HE is like a TE-like mode, but EZ may be slightly non-zero, and then EH may be more like a TM mode where HZ is not slightly non-zero. And then these LP modes, they're linearly polarized. And so actually sometimes these linearly polarized modes can be mapped onto a pair of HE and EH modes. Whether L is 1, like the azimuthal quantum number as you go around the fiber is 1 or above 1. Okay. So just to explain briefly what modes are going to be invoked in each scenario. So this is the single mode condition. So you typically have like this HE11 mode. Okay. But then once you go to V number between these two values, you actually get, in addition to the HE11, you get 3 more modes. Okay. And you also get this LP11 mode that I mentioned. And you keep getting more and more modes. And so at this point, don't try to memorize all the modes, but just to give you an idea that more and more modes are kind of coming online as you go to higher V numbers, right? So that's really the critical point. And then this showing you like what some of the field patterns look like for all these different modes. And so this is actually showing you there are quite a lot of different modes. And you go from like a small V number, something very simple, which basically looks linearly polarized, this HE11, to many, many more modes that get more and more complicated in terms of their spatial distribution. And this is just showing you what the dispersion is like for the frequency versus the V number. As you go to higher and higher V numbers, you get like more and more. But you can see that even though you get more and more modes at high V numbers, there's always like a gap between these different modes. So even if you're in a high V number and you have like tons of modes, like they're not all exactly the same frequency. So that means yes, you had a question.
One HE11 mode can be called as a single mode.
Yeah, that's a single mode. Right.
But the single mode is only numbers.
Yeah, there's only one mode, right?
But in the program,
oh, you're asking like why did I say there were two?
Yeah.
Oh, in the chart. Oh, yeah. So I should explain. So basically, the difference is just there are two different polarizations for the same mode. Sorry. So basically, what's happening is you can see everything's traveling this way, right? Mm-hmm. But you can also rotate this 90 degrees, and then you also have another mode. That's basically identical in terms of its form and so on, but it's just a different polarization. So of course, like we'll see later in the class that actually this so-called polarization degeneracy or what have you is actually very useful because now we can use not only like the individual modes in communication, but we can also use their polarization as well. And so there's actually a whole method of communication that's based around exploiting the difference in polarization of different, of otherwise identical modes. So that's very useful, of course. And so this is also showing you just, like if you took like a relatively large V number, and then you just looked at what is the intensity distribution of each of these modes, what do they look like? And so you can see basically this LP01 mode, this is like the lowest order mode, is typically like all kind of confined in the center and then it gradually reduces as you go out. But there's also this LP02 mode in which you basically have like kind of like a node right here, kind of halfway out to the edge of the system. You also have this LP11 mode where basically I showed you earlier, you have like something going like this and then like this, and then there's basically this whole dividing line in the middle. And of course, you can see that some of these modes, like the LP11 mode, you can rotate 90 degrees and you get another copy of that mode with just different polarization, right? So this brings me to the topic of polarization, so I'm glad you brought it up. Basically, what you want ideally is that when you send in polarization, like let's say it's going up in the x direction, or let's say x direction is this way. So it's going horizontally in the x direction. You don't want it to actually flip the polarization as it goes through the fiber. And that's why I was talking about adding the cladding is very important, but sometimes that's not enough, okay? Because sometimes in addition to the need for cladding, you may also have some basically random disorder in the fiber, and sometimes like during the fabrication process, it's not pulled perfectly smoothly, and so there may be some slight inhomogeneity in the quality of the fiber draw itself, and so this can actually cause some small power transfer over time or over distance as you propagate through the fiber. And so if it's a really long fiber like transatlantic cable or something, then it may completely flip the polarization or at least become elliptically polarized. And so actually like one of the key things we can do is actually we can break the symmetry to some extent between the two polarizations by creating slight ellipticity in the fiber itself. And so this is actually like deliberately breaking the coupling between the two polarizations. And so now instead of having two HE11 modes, we really only have one HE11 mode at a given wavelength, and then we have another HE11 mode at a slightly different wavelength. Now you can more easily distinguish between the two of them. So that's actually the real trick to getting like a single mode fiber, right? So you not only have to do like a small enough V number, but also a slight distortion of some sort, like ellipticity. Okay, so now this is not a typo actually. So this is called a preform, not perform. So what is a preform? So basically the idea of a preform for fibers is kind of interesting. So what you want to do is you create basically something that will become a fiber when you stretch it out. Okay, and so typically the idea is you would have some sort of chamber in which you can grow glass, and then the glass can be basically stretched through introduction of heat. And this is an example of this. And of course, there are many examples, so this is not the only one. But basically, the idea is you have this preform, and then it's being stretched out, and it's being drawn into a very thin fiber. Okay, so let me show you how this would work. So you basically take this preform, put it through like a heating zone, and this heating zone has to be hot enough to melt glass. So typically maybe 450 Celsius or higher. And then you're basically seeing it melt into very thin rod. And if you do this very slowly and carefully enough, then it can actually be achieved to basically have dimensions that are proportional to the preform, but of course much smaller. So this is how we can go from preform that's kind of a macro scale, something you can actually see and touch directly, to something with an inner core diameter on the order of 1 micron, which we need for the single mode fiber. And then you can actually draw it, and then if you let it go through a long enough distance past the heating zone, it'll actually cool off, of course, because it has a high surface area to volume ratio. So then as it cools off, then you can actually spool it onto like this roll. And then you can basically roll up like, many meters or even kilometers of fiber on a single roll, right? And so this is how you go from something that's easy to make to something that's actually useful for a lot of these applications. And this is actually showing you in more detail what all the steps of the fiber drawing tower involve. And so, of course, you have to take that preform, feed it into here, draw it down into the inline furnace. You have to measure to make sure that's actually the width you expected. And then you have to apply a buffer, cure it, and then you actually do get a real fiber out of this. And then you apply another buffer, and then you cure it again, and then you basically run this spool and tractor to keep things going. And you want to keep it going as steady and evenly as possible, because otherwise you'll damage the fiber. Oops, okay. So I think those are all the slides I had for today. I think we have a few minutes. Do you have any other questions?
The A, the figure A.
Uh-huh.
The V number goes to the 0 to 10.
Mm-hmm.
You said that if the V number goes up to the more than 2.4,
mm-hmm.
then it's going to be the multi-mode, right?
Oh, yeah.
If you change the multi-mode, then refractive index is going to be changed as like one type.
I see.
Not like smoothly.
I see. So, well, what's happening actually is that for the single mode, this is just showing like what is the effective refractive index. So when you have a transition from single mode to multi-mode, basically what happens is you create a second mode that has a slightly lower effective index, and it kind of like jumps in at 2.4, and then it kind of goes up again. And then you have another one jump in at like 3.8, I think it was. So if you go to this chart, it basically shows you, this is like, these are the V values where you get new modes jumping in. So the old one still varies continuously, but it's kind of more akin to what's happening here, where you see that the normalized frequency and the effective refractive index is varying smoothly, but now you have like, boom, like new one came online, and then it goes like this. So you keep like adding new modes. But the old ones like still kind of vary continuously. But I realize it's a little confusing at points. So I'm glad you asked that question. Do you have any other questions? Okay, well, thank you all for coming. Hope to see you on Wednesday.